Um, our next speaker, going from the frontiers of infectious disease and health to really the frontiers of space and knowledge itself, is David McComas. David is a space physicist at the Southwest Research Institute and principal investigator on NASA's Interstellar Boundary Project. David is an amazingly accomplished space physicist.
I'm Dave McComas, and Brock and Fernette invited me to come talk today and asked me to talk about my dyslexia. I countered that I'd be happy to talk about space physics, and we negotiated a partway deal where I'm going to talk about both. So that's the plan. I'm a lot more comfortable talking about space physics than I am about my dyslexia, but we'll see how it goes. So I'm 55 years old, and when I was growing up, I didn't know the word dyslexia. What it was called when I was young was slow. And it's an interesting term. It's not intended to be derogatory, but you needed some way to describe people who, in fourth grade, basically hadn't really started reading yet, like me. And so that was the term that was kind of widely used. I remember from second or third grade overhearing a private conversation that my parents were having, in which my mother said to my father, Mac, we're really, really, really blessed. We have 3 just very intelligent children. Now, the problem is there were 4 of us. And I knew who they were talking about. And my father immediately countered, now, Hazelin, it'll be fine. Dave's really tough, and he'll be fine. He'll make his own way. It won't be a problem. And my folks were incredibly supportive of me all the way through, and it was great. But, I was definitely the odd man out in sort of the family plan for how this was supposed to go. But I was doing a lot of other things, and so this is me in fourth grade. And while I wasn't reading yet, I was technically engaged in anything that came my way. I would disassemble and reassemble anything. I built things constantly. I invented constantly. I think I drove everybody nuts. So that they would, take me out and, give me experiences like this where I'd get exposed to this really high-level technical stuff because I was so interested in it and so good at it. And so I started to read in fourth grade, and that was good. I'm still a very poor reader, obviously, and can't spell. So, but I read enough to get by, basically. It's no fun, but I read enough to get by. But this, this allowed me, this technical engagement and reading a little bit, allowed me to start really doing a lot of other interesting things. So one of the interesting things I did, and this is a picture of me in high school. Now you can tell I'm already compensating because I'm compensating for the crew cut I had in fourth grade. But what you see here is that I'm selling jewelry. And when I was in junior high, I started making my own jewelry, silver and gold jewelry, and I started selling it across the Midwest at these various sort of weekend festivals and things. I actually made a lot of money doing that. I considered not going to college because I was making so much money making jewelry. And to prepare for this talk, I actually went back and looked at a few from last time. And I was really engaged by Jack Horner's talk, who said, what my difference was, he had a hammer. I didn't have a hammer, but I had this propane torch that you can see here. And it was pretty good, and so I could solder stuff, and I started inventing jewelry in really 3-dimensional, very unusual jewelry. If you come this evening and want to see some of it, my wife will probably be wearing some after dinner, or at the dinner. So, but I also got really turned on by physics at the time, because physics was so obviously intuitive to me that I felt like I could really just understand the answers in physics. You'd look at the problem and, oh, well, it's that, of course. And so I ended up going to MIT. Not exactly sure how I got into MIT, although I think it was because I had a torch. Because when I look back at it, I was a straight-A student in science and math, but I was not so good in a bunch of other classes. So my grade point average wasn't that wonderful. On the other hand, I'd run a successful company for 3 years, and I had this sort of entrepreneurial spirit that I think they thought was interesting. So I'd moved from slow to interesting. That was good. I felt good about that. And so I went to MIT for 4 years and got a bachelor's degree in physics. Now, while I was at actually, I'll go back for this. While I was at MIT, something else I got to be involved in was the Center for Space Research at MIT, which builds spacecraft instruments and studies various things in astrophysics and space physics, and they needed somebody who could do fine assembly. Now, I'd been making jewelry for 4 or 5 years at that point, and I could do fine assembly. I was really good at it. And so, because I had a torch, I could make jewelry, and then I could work on building spacecraft instrumentation. And so I did that for a couple years while I was at MIT. That made me pretty saleable, and when I got out, I went to Los Alamos National Laboratory for a couple years, where I worked as part of their space effort. They liked me so much that they said, after a couple years, well, we'll send you back to grad school. So I went and did a couple academic years at UCLA, and then went back to Los Alamos, where I finished my dissertation while working there. Spent 20 years at Los Alamos, actually worked my way up to the head of all civilian space at Los Alamos. In 2000, I moved to Southwest Research Institute, which, if you don't know it, is just an absolutely fantastic institution, one of the largest and most powerful and valuable nonprofit R&D organizations in the country. We have about 3,000 people. And that's where I've worked since 2000. This is a picture of my office. You can see here all of the things that a dyslexic needs. I've got a small table with chairs, and that's because I don't really read a lot, but I have a lot of people come into my office and we talk quite a bit. You can see that I have a TV and monitor up on the wall so we can actually put up PowerPoints and movies and things like that. And most importantly, you can see I have a big whiteboard. And the whiteboard is full of drawings and equations, and it's not a very good picture. I just took this last week with my phone, but there are literally 8 colors on my whiteboard. And that's there because I have people in my office and we're brainstorming all the time, and we're drawing and making things up and writing equations and figuring things out, and you need lots of colors to do that. So this is what my office looks like, and this is what I do now. So let me talk a little bit about space physics. Space physics starts with the sun. Some of my favorite data ever, this is from 1611. This is actually data on sunspots when they first started studying the sun in detail, and they started to figure out that the sun wasn't a constant object, but actually varied over time, and sunspots came and went. And you can see these beautiful pictures, this movie, as magnetic fields lift off from the sun and blow out into the space between the planets. Very active sun, material coming off, and it actually produces a 1,000,000-mile-an-hour wind we call the solar wind that fills the solar system and fills the heliosphere. I'll use the term heliosphere quite a bit. Helios is the Greek word for the sun. Sphere is the region of influence. This 1,000,000-mile-an-hour solar wind gets blown off all directions in space all the time. And you can see here very beautiful pictures. The sun is the size of the circle in the middle, and there's an occulting disk sort of to block out the brightness of the sun. And then you can see this matter coming out from the sun all the time, large coronal mass ejections and streamers and things like that, filling interplanetary space. So when I went to Los Alamos, one of the things they needed was somebody who could do precision work on a certain kind of detector that I had experience with at MIT, and I got involved in the Ulysses mission, which launched in 1989. This is the launch of the Ulysses mission on the shuttle. We had a large upper stage rocket that you can see there being pushed out of the shuttle bay, and then it actually went out to Jupiter and used the gravity of Jupiter to swing around and fly out of the plane of the planet, something we call the ecliptic plane, and over the poles of the sun for the first time. And what we discovered was fascinating. This 1,000,000-mile-an-hour solar wind was actually 2 million miles an hour over the poles of the sun, both the North Pole and the South Pole. Nobody had ever left this ecliptic plane where the planets are. But what we learned was, at least around solar minimum, that the wind was twice as fast over the poles. And so what you see here is the cover of Geophysical Research Letters. This is one of my papers that maybe has one of the longest lasting images in all of space physics. What you see there is a picture of, it's a polar plot of the solar wind speed, and you can see that it's a lot further away from the center, over the top and the bottom of the sun, and it's a lot closer in on the sides, about a factor of 2. And so that's the solar wind speed, and that's superposed on what the coronal and solar structure looks like. And it turns out that these bright things at low latitudes on the sun, called streamers, have much slower solar wind coming out of them, and the high-speed solar wind comes out of the polar coronal holes on the far north and south ends. There's more encoded in that than just that. The red and the blue gives the field direction and things like that. But this is sort of typical for how I've been able to communicate the field in my own area, kind of putting together the different pieces of knowledge into a single graphic that you don't, I mean, if you're a space physicist, you don't have to read the caption. I mean, you can look at that image and say, oh, fast wind, coronal holes, and you get the whole thing. So that's the kind of thing that I think my mind has been well suited for. We've also studied the Earth's magnetosphere. There's a region of space around the Earth that's dominated by the magnetic field of the Earth, and this solar wind interacts with it. This is a movie, artist's conception of solar wind coming in, striking the Earth's magnetosphere. It actually couples into the magnetic field, couples energy into the magnetosphere, and that's what creates the aurora borealis. And so actually this 1,000,000-mile-an-hour solar wind that's been coming out from the sun and traveling all the way from the sun comes in, couples with the magnetic field at Earth, gets dumped down into our atmosphere, and makes the aurora. And that's why you see aurora. Okay, all of that, though, is just this tiny little piece of what space physics is down in the lower right of this graphic. You can see in the box about how big that is. The big picture of space physics is the heliosphere, this region of influence of our sun. And so the solar wind actually blows out all directions in space all the time, and it inflates a bubble in the interstellar medium. Outside, there's also ionized gas, neutral gas, magnetic fields, and there's this bubble that's produced by sort of pressure balance between the solar wind on the inside and all the stuff on the outside. And that makes an interaction that's really, frankly, very important for us. This is the most technical graph I'm showing. This is galactic cosmic rays at 100 million electron volts, typical cosmic ray energy. These are very damaging. There are a bunch of doctors here, and you can imagine 100 MeV particles coming through biological matter. It's not a good thing. But fortunately, the heliosphere, as you can see in this graph, basically shields out about 90% of those galactic cosmic rays. And so we're protected in the inner solar system by this interaction of our solar wind at the edge of the heliosphere. If it weren't for that, we couldn't really think about human exploration and space flight. Certainly, we wouldn't be able to go to Mars, and probably it would be very different for our lives here on Earth. And so there are some of us who think that this kind of shielding of the heliosphere is actually a requirement, perhaps, for life around stars and other planets. Just like you may need liquid water, you may also need the protective shielding of an astrosphere around another star. So really very, very important for all of us. And we know that these things exist around other stars. These are beautiful pictures of astrospheres. The problem is that the interaction here isn't strong enough to give you bright emissions like this. And so we had to find another way to observe our own heliosphere, and this is how we do it. The solar wind, these are individual protons coming off, solar wind coming off radially outward, filling this space between the planets. It gets out to the outer reaches. It's magnetized. These are charged particles, so they gyrate around the local magnetic field. But there's also cold material, neutral atoms coming in from the interstellar material all the time. These are the blue things that you see. And occasionally, an electron hops across to one of these things that came out of the sun, and it goes zipping off whatever direction it was going. A few of those come back past the planets, come right in towards the center part of the solar system, and can be captured in our instruments in Earth orbit. This is the Ibex spacecraft capturing one of these individual atoms that's come 10 billion miles, I'd like to think of it as the 10 billion mile hole-in-one, coming 10 billion miles from the outer reaches of the heliosphere and let us measure it. And so we decided we'd try to propose a mission to NASA to measure those individual particles coming in from that great distance. So we won. We proposed, a small team of us proposed, and we ended up building a spacecraft. It's a very small spacecraft. These are just some pictures of the team working together. This is Susan Pope, my system engineer, and some of the technicians. This whole spacecraft is only less than a meter in diameter. It's less than half a meter tall. It's less than 100 kilograms. So it's a very, very small spacecraft. The reason that it needed to be such a small spacecraft was because the other thing that NASA gave us, along with the $100 million to build the spacecraft and do the mission, was they gave us a launcher. But the launcher only goes to low Earth orbit, and we had to go almost out to the moon in order to see these individual particles. So we had to think out of the box. How do you get from low Earth orbit almost out to the moon? And the answer to that, of course, is you convince NASA to let you put a rocket on top of their rocket.
Ibex was launched in the fall of 2008 from Kwajalein, a remote island far out in the South Pacific.
So this is an artist's rendition of our launch. We're actually the rocket hanging on the bottom of that aircraft. It gets dropped off, the airplane pulls away to a safe distance, and once the airplane's a safe distance away, stage one ignites. So this is the launch vehicle they gave us. takes us up in 3 stages to about 200 kilometers altitude. And what happens is you go higher and higher, you're working your way through the atmosphere, and you break away, you burn out parts of the rocket and throw them away, and you move on to smaller and smaller parts of the rocket. There's first stage burnout in the start of the second stage, probably about 80 kilometers now. You get up above most of the atmosphere, and you want to dump the rest of the mass. So pretty quickly, you've got to remove the fairing. There's the fairing. Once that's gone, you burn out the second stage. You're on this very small rocket, this third stage rocket that's going to take you up to a couple hundred kilometers. Here's the third stage. It burns out at a couple hundred kilometers. There are cold gas jets on it that point this entire spacecraft and then the dead third stage, spin us up to 60 RPM. At that point, we owned the launch. And so we discarded the third stage. And then we had a very specially balanced mounting ring that we provided because the third stage wasn't spin balanced well enough to be able to separate properly. And then we had our own solid rocket motor that we bought actually 2 of and tested one and then burned the other. And we used this solid rocket motor basically to lift off from low Earth orbit and go out to the distance, nearly the distance of the moon, where we could measure those individual particles coming in from 10 billion miles away. So here's what we found. We found that the heliosphere, which we drew here, which is this sort of bullet-shaped thing, is actually wrapped around by the magnetic field from the interstellar medium, that magnetic field squeezes on it, almost like bungee cords would squeeze on a beach ball as it pushes its way through this magnetic field. And we discovered this ribbon. What you see here are bright emissions of these individual neutral particles, about 3 times brighter in the green and the yellow than anywhere else, any other direction you're looking out in the sky. And it correlated with the place where the magnetic field was stretched around the outer boundaries of the heliosphere, what we call the heliopause. And so this was completely unexpected. There were no theories, there were no models, there was nothing in advance of these data to tell us that there was this sort of weird interaction going on. Now, for those of you who are scientists here, you know it's hard to publish. You know it's really hard to get published in Science. But I got to tell you, it's really, really hard to get a special issue of Science and get the cover. This is the cover of Science on the special issue that we had in November of 2009 with the first results from Ibex in a set of 6 papers. For those of you who aren't scientists, on the right side, what you see is me receiving an award on behalf of the team from Charlie Bolden. He's the NASA administrator. And so this was really, big picture important science that we got to discover. Okay. On each of your tables, there is a yellow envelope with an Ibex sticker on it. Open your envelopes, please. Just take those out and pass them around. There should be enough for everybody to have one. Okay, so how does Dave's brain really work? This is a lenticular. A lenticular allows you to encode multiple layers of images on top of each other. And if you tilt it back and forth, what you see is the different images. There are actually 5 images here. And so those individual particles we collect in 5 different energy bands. The color indicates the intensity of those particles. As you tilt it slightly, you see different energy bands, and that tells you the energy of the particles. And what you basically see here is what we call a mole-wide projection, where we've taken the sphere of space looking out around us, and we've opened it up and put it onto a flat surface. So this is effectively 3 spatial directions, 3 spatial dimensions, 1 energy dimension, and 1 flux dimension. This is a 5-dimensional rendition of our data. And this is, to the best of my knowledge, the first time that space data or any data has been encoded onto a lenticular. They're usually used for sales. People put cool things on that, you could be sitting on a beach or something like that. But it's especially cool. We made 50,000 of these. Actually, I was told that when they showed up at NASA, somebody rushed several of them over to the White House because they wanted the Obama daughters to get copies of these and look at them. But as a scientist, this is a way to encode our data where we get to look at all 5 of these dimensions at once. And to some extent, this is how my brain works. So, dyslexic advantages, sure, probably lots of them. I think being dyslexic can make you tough. You know, you use what you have. No point in whining about what you don't have, you use what you have. I think it can make you dedicated and really a hard worker. I think it can make you very independent. I think it can make you say, I don't really care what people say can't be done. It doesn't really matter what they think can or can't be done. I think it allows you to see the big picture sometimes. I think it certainly helped me synthesize data visually, spatially, temporally, and in flux and other sorts of dimensions. I think it allows a lot more innovative and entrepreneurial kind of spirit, at least in some dyslexics. I think it's helped make me a lot more collaborative. I mean, what I do most of the day when I'm not doing what pays the bills, when I'm doing the fun part of my job, is I'm at the whiteboard with one or two people, and we're sort of brainstorming and trying to figure out something we don't understand yet. I think it's helped with verbal and interpersonal skills. This is something that's not physiological. I think it's helped me understand the value of different strengths and made me a much better team builder. Because everybody doesn't have to be the same, and you don't all have to be good at the same thing in order to be smart or good. In fact, in a team, it took hundreds and hundreds of people to do the Ibex mission. You need people with all kinds of different skills, and you need them to work together well. And so, I think that there's kind of a diversity of thinking that is easier for dyslexics to understand why that might be good. I think it helps with, getting the big picture vision, see what's needed, and sometimes the leadership to do it. And so, what I say is, hell, if you got it, go with it. Let dyslexia set you free. So in our case, the journey begins again. This is my wonderful family. My wonderful wife, Rochelle, is back there, who helped me through school and other things my whole life. And our three wonderful sons. The one in the Spurs t-shirt, remember we live in San Antonio. The one in the Spurs t-shirt is my youngest son, Orion, severely dyslexic. We had him tested at, I think, age 6, and they said, well, maybe he'll never read at all. Through a lot of hard work on his part and Rochelle's part and others, and a lot of accommodation, he's now in college. The other two, who are sort of divergent learners, have also made it through college. And so, kind of our journey began again. I never actually thought of myself as dyslexic until Orion was tested and diagnosed, and it's like, well, of course, sure. That's what I've been doing. So with that, I'm going to end, but I want to end the way I always end talks that include Ibex data, which is with a thanks to all of the outstanding men and women who made the mission such a great success. It takes a team of hundreds and hundreds of people working together to make this kind of thing happen. And so I thank them, and I thank you.